Yep, I'm recording now. And so this is our, again, fan pattern around, this is M32. The central part here of Andromeda is very bright. And this is an ultraviolet image of Andromeda, actually, that we are centered on. And today we're observing, right now, we're observing one of these light purple masks that's oriented more or less horizontally, like this, sort of not at too much of a tilt. Yeah, I was going to show you some pictures of Andromeda. Close-up Hubble pictures of Andromeda. Not close-up, it's just about as far away as it is, but.
So this is Prem Singh from Future Hope.
Hi, Prem. Yes, go ahead, please.
Yeah, just the other day I was thinking about the non-baryonic dark matter and possibility of black hole made up of dark matter. So just now you said that the dark matter, possibility of dark matter, black holes of dark matter is not possible. It will break the disk of galaxies.
If the black holes are too big, if the black holes are very small meaning low mass, then there's still room for that. So asteroid mass black holes, primordial asteroid mass. Remember, I showed you a paper that we had written recently. I was a co-author on this paper that shows that primordial asteroid mass black holes are not ruled out by the current evidence. But solar mass black holes the mass of the sun, those are ruled out. Those are too disruptive.
So is this small black holes are non-baryonic?
Mm-hmm. These small black holes would be baryonic. They would be baryonic dark matter.
My question was, what is preventing so large mass of dark matters to form black holes? The black holes purely made up of non-baryonic matters.
You know, so it depends on the nature of that non-baryonic matter, right? So to form a black hole, you need a very high density of material. That's the most important thing. And generally, matter in the universe is very low density. Most of the universe is very, very low density. One of the exceptions is star. Center of a star is an exception to that. So a natural way to form black hole is through the death of stars, because you built up the high density needed. So it's difficult for black holes to form spontaneously in the universe because the density is simply not high enough.
So as far as I know, there are large mass of non-baryonic dark matters are there.
DCD readout complete.
Outside the halo region of the galaxies. So
That's
why
correct.
don't they?
Yeah.
So
why don't they form black holes? Because the density is low. Even though they're very large in mass, the density is low. And really, to form a black hole, you need high density, and that's the key.
But they are influencing the way of other stars.
They're indeed influencing the motion of stars. In fact, that's how we know about the presence of this dark matter. It's because of how rapidly galaxies are spinning, not just stars, but also the gas and dust in galaxies. So these are excellent questions, Prem. These are fantastic questions. I mean, I can see that there's no question in my mind that if you decide to put your mind to astronomy, you will make a fine astronomer.
So I'm not a student, actually. So I'm not a student of Future Hope, actually.
You're not.
I'm looking out. Yeah,
tell me your role at Future Hope then.
Yeah, I'm actually looking after the computers and all that. So
I see. Where did you study? Which school did you study at?
So, actually, I studied from Bhawanipur Education Society College.
I know that college very well because I used to live in Lansdowne Road, which is very close to that. Where did you go to school, though? That's a college. Where did you go to school?
Cathedral Mission High School.
Cathedral Mission, okay. No, and you're doing wonderful work at Future Hope. So I know you'll be an inspiration to the students at Future Hope. So those are great questions.
Thank you. Thank you very much. Thank you.
Arena, thanks for joining. Would you take a moment to introduce yourself, please? Oh, yeah, you're welcome. Thanks. Yeah. Arena, go ahead, please.
Can you guys hear me?
We can hear you, yes.
Okay, great. Hi, I'm Marina. I am one of the observing assistants at Keck, also known as telescope operators. So that's a more common term for us. So I don't know how much you know. I'll just tell you what we do. There's about 10 of us here at Keck. As you know, we have Keck I and Keck II telescopes. So it takes about that many of us to run the Keck telescopes every single night. So my primary responsibility is to ensure the safety of the telescope. So that includes things like, when I'm slewing a telescope, so moving it around, making sure it doesn't hit anything, it goes where it's supposed to. Looking at the weather outside, so keeping an eye out on the clouds, making sure it's not all of a sudden raining in the dome. We don't want that. We don't want, anything hitting our big shiny telescope mirror. So it's very important if any weather is coming in, whether it be rain, snow, or really, really strong winds. We don't want that, anything like that affecting our primary mirror or anything really in the dome. So it's my responsibility to keep an eye on that and close up the shutters, making sure that the telescope is safe from the outside elements. That's basically it. Do you want me to say anything else, Raja?
That was very good. Thank you. Thank you very much. There's a very essential partnership between visitors to the observatory, like Doug, Ivana, and myself in this instance for this experiment, and folks like Jim and Arena who work at the observatories. It's teamwork. I mean, right? We are all trying to get the best science out. We're also trying to get the best science out in a cumulative way, not in a way that breaks the telescope tonight. We want to continue to get good science out from the telescope. But it's a very essential partnership. And it's something that I've been privileged to be part of for the last, 25 years, more than 25 years. And so the conditions on the summit are very harsh because you're at 14,000 feet. And it takes a while for the body to adjust to that reduced oxygen level. And yet, at least now, the way the telescope runs, until UNO is in place, you need people on the summit. And so it's a very, very essential and difficult function that you're performing there, Arena. So thank you for that. I'm looking at our masks here, and in 20 minutes, the stellar traces are quite faint. Ivana, the stellar traces in these M32C masks are quite faint, and the seeing is okay. It's not terrific. I should do a calc seeing here. I bet it's 0.8 or so. Yeah. The image quality is okay, right? It's not great because it's that very high MS. So 0.8, yeah. The best is this. Look, seeing is more like 1. So I'm wondering, we can do a couple of things. We could go longer, or we can see if it's worth doing a Myra. I'm actually wondering if it's worth doing a Myra here.
Yeah, I suppose you can ask the OA. I cannot comment.
Yeah, so I suggest we do a Myra because we're actually a little bit ahead of time. We could do a Myra, come back to this mask, see if the stellar traces look better. Now, some of these.
Interrupt the current sequence when this one. You want to do the full 1 hour?
So it's on its second 20-minute exposure. I'm thinking I'll stop this at 10 minutes. And so we have a 20, a 10 in this, not so good seeing, do a Myra, see, and we'll do a Myra maybe a couple of hours ahead, not here because we'll be staying on this for a little while. And then let's see if it improves the image quality. If it doesn't, then we know we'll have to take longer exposures. We won't be able to observe 7 masks tonight. If it improves it, we might be able to come back to our original plan. Does that sound okay, Arena and Jim, in terms of, because what we're looking at in this first 20-minute exposure is not so great signal to noise, and the traces are not that great. The stellar images and the alignment image are not so good. So I'm thinking I'll truncate this exposure at a total of 10 minutes. So we'll have finished 120 and 110. And Jim, I should probably Control-C out of this sequence before I do anything else, right?
Yeah, you want to Control-C out of the sequence before you
So I've
end
done
the
that.
exposure.
And I'm going to head the I'm going to change the exposure to 600, apply. And then I'll make a note in the log in just a moment, but I think we should do a Myra. I think we should do a Myra 2 hours west of here, please. Ah, that is so sweet. So Rina, in about 2 minutes, we'll please do a Myra 2 hours west of this mask, and the position is marked, so I assume it'll be easy to come back to this. Thank you. Thank you. There's nothing magic about 600. I suppose I could stop it anywhere, but there, I'm done it. I'm going to stop it at 9. All right, Marina, so in just a few seconds, you'll have the telescope to go off and do an alignment. And while you're doing a Myra, while you're slowing, if it's okay, I'll just change it to 0th order because we'll need to come back to that for a course alignment. Sorry, fine alignment.
Okay, sounds good.
Okay.
Exposure complete.
Please start the slew and I'll do a go 0 here. And this time I'll remember to hit apply. All right, here we go. I think it's a good decision, Ivana, to try and improve image quality. Yeah. All right. So what we're doing right now, what Arina is doing right now is going off and she's going to refocus the telescope to see if we can get sharper images from the telescope. And the refocusing is a very interesting but elaborate process. And I'll show you a screen in which you can see what's going on. In this screen, you'll be able to see, you can see the telescope's moving. That's why these stars look like they're streaming across. The telescope is moving.
DCD readout complete.
Yeah, it got a little better the second exposure, even though it's a shorter exposure. It got, images look a little better, but it might be my imagination. It's not dramatically better. The sky got darker because it's half the exposure time. But this one.
Yeah, it looks pretty similar to me. I mean, I saw this trace.
You saw that before,
but
yeah.
This object.
It's very faint and it's a longer slit, so it could have something on the. I'm also thinking that some of these slits will be, some of these objects, this is one of the M32 masks, so some of these will be on multiple masks. So that's the other thing. But still, I think it's worth trying to improve image quality. So the way the telescope is focused is Rina is going to go to a bright star and they take the Keck mirror is made up of 36 segments. Yes, please. Thank you. So MIRA, M-I-R-A, stands for mirror alignment. She deliberately puts the segments of the mirror out of alignment so she can bring them into better alignment through this process. She takes them out of alignment one way, out of alignment the other way, and then adjusts what is called the secondary mirror. I think one time we had shown you a model of the primary mirror and secondary mirror. It adjusts the position and tilt of the secondary mirror in order to achieve sharper focus. Now, if you look closely, you'll see that every image of the star went from a single dot to becoming multiple dots. Can you see that? And that's because the Keck telescope is made up of 36 segments. So each star is now showing 36 images. And you'll see that appear here as well in a moment, as soon as Arina takes some images with this. And I'll zoom in when that happens. So this process is called MIRA, M-I-R-A, which is, of course, a common name, especially where you are, Future Hope. MIRA is a very common name. but in Spanish, mira means look, see. But in this case, MIRA is an acronym for mirror alignment, MIR for mirror, A for alignment. Can you see the 36 images of a star right there where I'm pointing my cursor? I'll show you a more detailed version of that in a moment. It's taking
Exposure complete.
So by now you know that when it says exposure complete, can you hear the sounds where it says exposure complete and Future Hope and Hunter and
CCD readout complete.
Okay, are you getting those voices
Yeah, we can hear them.
over Zoom?
Mm-hmm.
Okay, thanks. And so as soon as the readout is complete, it will show you an image. So, oh, it should have shown, displayed it already. So I'm going to zoom in here and see what I mean. Do you see multiple images of a star? And the reason there are multiple faint patterns like that, because there's more than one star. And each star forms a pattern like this of 36. These are the 36 segments of the Keck telescope. And if I move around here, this is a very dense star field, Arena. Wow. Must be some kind of star cluster because we have lots of stars here. Wow, look at these two. They're two stars that are perfectly separated by one segment length. Isn't that right? Isn't that what's going on here? There's a fainter star at the bottom and a brighter star. And I think their separation is exactly equal to two segments.
Two segments, yeah.
Two segments, not one. Huh? Because you should have 4 on a side and we've got 6 on a side here. That's beautiful. How did you arrange this, Arena? This is amazing.
Exposure complete.
But you can see that the individual segments don't produce perfect images because, you know, they're slightly out of
CCD
shape.
readout complete.
By moving around with all this, I hope I'm not interfering with anything.
No.
As long as I don't touch things. All good, okay. Hunter and the Future Hope students, why do you think there's a hole in the center here? Why isn't there one more star image here? Any guesses? Go ahead.
Sir, no, I have no idea.
No, it's because there's a gap in the segments. There's 36 segments and there's a hole in the center of the actual mirror for the light, for the focus light to go through after it strikes the secondary mirror in order to go to what is called Cassegrain focus, which is a particular focus of the telescope. So that's why. That's the actual pattern of
Thank you, sir.
segments. Yeah, sure. Perfect, thank you. And I will get ready to do, I'll make sure the instruments in 0th order. 1200G, correct grating. So I will just go to fine align and be ready to start a fine alignment after you give me the word. So this one is saying the average seeing was 1.2. I don't know if I believe that, but at least the stars don't look that sharp. Look at that. So I think the Myra was really, really, really helpful. So thank you. Wow, you went from 1.2 to 0.5, and that makes a huge difference. All right, moment of truth. We hope for sharp spikes at the centers of each of these boxes. 0.5 is what we want, Irina. That's exactly the kind of seeing we need for this project. 1.2 is not. So it'll be interesting to see. This Myra was done 2 hours with.
Exposure
So
complete.
see what it is at this location. If we're talking about just high MS effects, then there's nothing we can do about that. But it's good to know that the Inherent seeing is very good tonight.
DCD readout complete.
I see that. I see that. That's really dropped on the guide of that frame. Oh, wow. Better. Much better. Send moves only, or what do you think, Jim?
Yeah, I'd retake it. It's almost it's 0.4 arc seconds.
Oh, yeah, yeah. Okay, okay. The Y move. Okay. This was a good Myra to do. Not just because you found two stars that were separated by 2 segment spacings, but that's a dramatic improvement in image quality, 1.2 to 0.5.
Exposure complete.
So readout goes much faster when it's doing these alignment images because it's so smart. It reads
DCD
out only the
readout
part of
complete.
the CCD that includes just the boxes, even faster than in imaging mode. Imaging mode reads out the whole imaging area. All right. This is all good. So nothing to do here. So I'm going to go back to I'm restoring this, apply, and I'm going to take 3 more exposures here, except they won't be 20 minutes, but I think it's worth doing 3. So I reset the object name, Jim, and I'm going to do a GuhaThakurta, and I'm going to increase this a little bit. I'm doing 3 times 15, yeah, with the better seeing. Okay.
All right, we're seeking.
Okay, so I've started the WFFCS thing, so let me
Right.
clear samples. Let me. Claims it's ready, or it hasn't refreshed. Ah, hadn't refreshed, okay.
If you want to calculate your seeing from your science
point.
image.
Good point, thank you. From the this image. Point 0.8, 0.7, 0.7, sorry. So hopefully as the MS gets smaller, we'll reach our 0.5, but this is good. This is still a dramatic improvement compared to where we were. All right, so I'm going to try and figure out how to.
Yeah.
Okay, started. No, not yet. Now it started. Oh, lockout.
It's just erasing.
Just the erase. Okay, okay.
Yep.
So it temporarily closes the shutter during the erase.
Yep.
Okay. All right. This is good. I'm guessing this is just the high MS. This elongation is because of that. It's actually a very crowded part of the sky. So these neighbors that you're seeing, this is very common in this part of the sky. Yeah, a lot of elongation.
And those squares are the alignment
boxes.
stars.
They're the alignment boxes, yeah. Do you see the neighbors of this star all around?
Mhm.
Faint neighbors. But the stars are definitely elongated, and they elongated along the, can we tell?
There is some wind shake tonight, so if they're elongated along the elevation axis, be it.
I'm also I'm confused about one thing here. This mask is meant to have a position angle of 90. And I'm looking at the northeast compass rose. It claims that the slits run north-south. Am I misreading that?
91, that's what they're.
Yeah. Okay, yeah, that's what it should be. It should be about 90. But do you see what I mean about the compass rose in the upper left of Ginga?
Yeah.
That doesn't look right.
What is the one behind Ginga showing you? It looks like it's the opposite.
Yeah, exactly. Well, exactly. This compass rose here, right?
Yeah,
not that one, not that one. Sorry.
I was.
Where did it go? I know what you mean. This one.
Yeah.
Yeah, this is correct.
And that's why that makes more sense with the elongation because it's.
Yeah, it's along the
east-
elevation axis.
East
Yeah.
is along elevation.
Yeah, and you can see the elevation azimuth. Yeah. Okay, so there's hope that in the later exposures things will get better. I'm actually going to go to 320 minutes for this because I think when the seeing gets better, I can afford to cut the exposure time on those masks. This one needs the longer exposure times. I'm trying to move my cursor from my laptop to the main monitors, and that's not working well. But I'm going to change this. Okay, Jim. So what I want to do is make some notes in the observing log. But at least we've done one thing right here, which is we wanted to align the slits and mask along the parallactic angle, and we've done that. Otherwise, there'd be greater light losses. This way the stars smeared out, but there's not losing light.
Yep. That's nice.
So which window is, oh, okay, I'll let you take over.
I don't know if we started one.
I don't think we started it. Yeah, it's on the far right.
It can be in whichever one we want. We can put it with the alignment tool if you want.
Okay. So I'll show you what Jim is doing. He's in this window. That's a picture, by the way, of DEIMOS on the right. This is the spectrograph that we're using. this big metal cylinder. Go ahead. Were you going to ask a question there, Future Hope? I see a microphone.
Sir, I
Yeah.
have a question.
Yes, please go ahead.
Sir, is there iron core in the moon?
That is a very good question. Is there an iron core in the moon? There is
Because
a
there, that's why.
so there is a core in the moon. Is it a molten core in the moon? I don't know. Do you know, Ivana? No molten core? All solid? Is it iron though?
With it seems to be made of iron and nickel.
I see.
It has to be similar to the Earth, yeah.
So Ivana's saying that there was she heard a talk recently at Princeton about people not really knowing what the center is. But Doug, you said you found iron and nickel as
Yeah, just a casual Google search.
Google search. Okay.
It's from the NASA website.
No, but that if there's an expert who's saying that there's no consensus, but yeah, in general, it's very hard to know what the interiors of planets and moons are made of because we can't directly collect samples. This is true even for the interiors of stars. We can tell what's going on in their surface, but much harder to understand what's going on in their interiors. Same thing for the ocean. We can understand what's going on near the surface of the ocean, but the deep ocean remains pretty largely unexplored. So let me see. I was going to look into something very quickly. Yeah, the elongation, Rob, the elongation of the stellar images is not due to guiding. We think it's because we're looking very low in the sky. When that happens, the differential refraction of light, light of different wavelengths, first of all, will bend by different amounts. That can cause elongation. But in this case, since we're taking guider images through a filter, is the reason wind shake, or what do you think is the reason for the elongation along the elevation axis? This is a question for Jim and Karina.
Karina, do we have a lot of wind shake tonight?
Sorry, I was not paying attention. What was the question?
Is there wind shake?
Yes, we are getting some wind shake from.
Okay. Does that tend to be along the elevation axis, or?
Yes. The telescope will act like a sail and kind of
oscillates
like this.
Got you. Because it's looking in. I see exactly what you mean. Okay. So it's gusty, and that's what's causing this sort of. Yes, so Rob, technically it is due to guiding, but it's happening at a rate that's so fast that we can't keep up with our guiding. If this were a slower oscillation of the telescope, we could have kept up with it, but
Sure. Thanks.
Sure. Am I interpreting that correctly, Jim and Arena, that if the telescope were oscillating much more slowly, we could keep up with it, right? But it's happening so quickly with the wind shake and stochastically that we can't keep up.
Yeah, our guiding corrections don't come that fast.
That fast, yeah, okay.
Yeah.
So about 1 a second?
About 1 per second, yeah.
Oh, okay. So if the wind were to die down, we would get better image quality. Okay, so what I want to do, Jim, is I want to go to the observing log and I want to take some notes. And I seem to remember that
If you go all the way to the right-hand side, so use the slider to move all the way to the right-hand side.
got it. Okay. I'm just moving it out a little bit. Okay.
And then where it says comments, you just double
just
click
just
in that.
click on that. Okay.
Yeah.
So what I want to do is at the top of the night, what we did was we just took bias, focus. Okay, got it. I'm just scrolling.
We started
So-
with the RLI, right?
We started with the RLR right there, but before we did that, when we did a Myra, I want to make a note that the Myra that was done just before this had what, 0.5, I remember.
Mm-hmm. Yeah.
Hello, sir.
Yes, hello.
I have a question.
Go ahead, please.
So, can we call that any energy is a part of matter?
You know, matter and energy are supposed to be interchangeable through Einstein's famous, very famous formula. You know the formula I'm talking about. E equals mc squared. In that, just give me one moment. I want to type in this comment. I'll come right back to you. So we measured a Myra seeing of 0.5. You guys measured the Arena, you measured this. And then when we did the first alignment, we measured the seeing again. And there I thought it was, what was it when we measured the seeing there? It was worse, right? I thought it was point.
Sir,
Just one moment, sorry, just one moment. So this was a seeing fine alignment. And there the seeing.
It's 1.2, I believe you said.
At one point it was 1.2 when was that? That was that during the alignment that we saw that? Must have been, right? How else? It must have been post alignment. Okay. So seeing full width half maximum was 1.2. And then you did another Myra after the, so I'm going to just make a note saying this was truncated. Okay, so this, sorry if I'm making you motion sick with all the, so this exposure, truncated to Myra. And then in that Myra, the seeing full width half maximum was back to 0.5. And at some point we measured 0.7, that was during this alignment. .8, I guess, is what we measured here. Sorry. Don't know what it's doing here. It won't let me copy paste something.
I don't think it does let you copy
Okay.
plate.
All right. I'm just going to write, I think I should write wind shake here. Sorry, I'm just Typing all this in. Okay. Just want to put all this notes in here, and then this is scrolling all the way down now. I guess it hasn't read out the first of the 20-minute exposures yet, right? Don't think it has. Yeah, it hasn't.
That's right.
Thanks. Thank you for giving me access to this. I never remember how to get there, but thank you. So I go back here and back to this window. You'll see that it's nearly done with the first 20-minute exposure, and the image quality is better, but it's not perfect yet. And sorry, I cut off your question. Please ask your question now.
Sir, we have known that energy can be converted as matter. So our thoughts, the thought process is also energy. So can we say that our thoughts are a part of matter? Because it requires.
Yeah, I don't know how you would say your thoughts are energy. That's a tough one. The kind of energy that Einstein was referring to when he was thinking about E equals mc squared is really light energy or radiation energy, photon energy, is interconvertible to particles. It's a good question. I don't know how to answer your question. But the interconvertibility of matter to energy is something that is very much at the essence of special relativity and E equals mc squared. It's a great question. Thank you.
Thank you, sir.
Thanks.
Sir, it is our lunchtime now.
It is your lunchtime. Well, wonderful seeing you all again. I'm going to say goodbye to you, but please reconnect when you get another chance. We'll be on the telescope again tomorrow night. Tomorrow night's our last night for until the end of the month. At the end of the month, we'll have 2 more nights again.
Bye, sir.
Bye-bye.
Thank you, sir.
Thank you very much, sir.
Thank you. There are a few others who have connected who we haven't had a chance to hear from, but yeah, when they mute themselves, there's a lot of excitement and activity there around lunchtime.
They seem very sweet.
They're so nice. Yeah, they're super nice. So Prem Singh was asking these. Yep. Yep. Oh no. Okay.
Exposure complete.
Okay. I'll make a note. And I think we stick with this mask. It's better that we, better that we get, we're on the second of the, second of 3. Oh, it's reading out. It's reading out the first of the 20-minute exposures, but it's good to know. I'll make a note. Thin clouds. No, we didn't. Just staying with the same one. What we did was, yeah, exactly. So we did 10 and, sorry, we did 10? No, we did 20 and 9 minutes. And then even though the image quality improved, still we see a lot of elongation. So I just decided to do 3 20 minutes again on this. So let's finish the first of the 20. We should see some improvement because it did improve from 1.2 to 0.7. It'll read out in a second.
DCD readout
it's going to show up. I just changed I'll change the stretch from here. So let's see. It's just set up for imaging mode. That's why it looks bad like this, but there we go. There's our spectra. Just zoom out. That's an alignment box.
Some faint traces.
Some faint traces, yeah.
Depends though,
Yeah,
if you fiddle
with this. Yeah, absolutely, absolutely. It's a little better, but you can see a little bit more. Let me. It's making it a little darker. Tough place to work. I tell you, this N32 has a crowded field. This region generally of the disk is crowded. So, you know, something like this, we should be able to pull out a velocity.
Yeah.
And there are some stars that are brighter.
Yeah.
Yeah, those things I think we should be able to get. So we can move around. Yeah, go ahead. You want to pan around? So middle button lets you move pan. What is it? So if you click on the middle button here, it centers that. How are you zooming out? Right button?
I'm just.
Oh, I see.
scrolling.
Scrolling. I see. Oh, that's great. Okay.
I'm still figuring this out though.
That's okay. You can use the plus minus too if you want to zoom in. It's also.
Okay, so on DEIMOS, is this the blue chip on the top?
No.
These are the red ones.
Red ones on top
Okay.
and blue ones at the bottom. The density of sky emission lines is a little lower at the bottom. You could see much more trace, I feel, than before. When the first one came out, I was sort of shocked. There's very little to see. These are serendips, absolutely. You see lots of them. And it's satisfied the isolation criterion in the sense it's outside its seeing disk.
Yeah, well, I guess this is probably clearly, hopefully the primary.
Yeah, that should be. And it'll know. I mean, from the design, it'll know if that's the primary or that happens to be a serendip that's brighter than the primary. But, you know, it looks a little bit close to the edge to be the primary because, you know, minimum slit length and all that, half of that. I suspect one of the other two is the primary. But this is not bad. Look, I mean, there's quite a bit here.
I move this that way.
What are you trying to move?
I was just trying to.
Yeah, if you just left click on this window, it'll just move the center to there. It takes one click to register that it's moved, but then it. I'm not seeing a lot of background galaxies, which you want, right? Because the probability of finding one is low.
Yeah.
You can see the A band a little bit.
Yeah, I was kind of trying to see if I could, even in these faint traces,
See the calcium triplet.
see, prominent spectral features like the toric bands, but I'm clearly having difficulty controlling.
Tell me what you try to do. I might be able to help. You want to zoom in on a section? You want to zoom in on the.
Yeah.
Okay, so I find middle click, which is clicking on the wheel, is good. So this is the A band in this star. That's 7600. You see how the star disappears there? That's the A band. And now we might be able to see the calcium triplet if I. Which one?
Here?
Yeah, that's the A band. That's the A band. So if I move up a little bit from there.
There? For that star?
No, I was looking for this star.
No, but what about this one?
It's A band.
Yeah.
It's A band, yeah. But it's a fainter star.
Yeah.
I was going to look at this star and see if we can see its calcium triplet. And it would have to be in the upper part. Part of it is, this is the 1200 line grating and higher spectral resolution, of course. We'll find it in a moment. Let's see, where is it? So, still going. So this is 8660 for this star. Can you see the calcium triplet right there? You see the gap there? I think that's it.
You recognize it because of
Yeah.
the skyline?
Exactly. And then the other calcium triplet line is somewhere there. Can I see it though? I don't think I can tell if it's there. Now it's a long way. Some of these stars are a long way negative velocity. It could be this thing here is one of the calcium lines. I see some. It's hard to tell, you know, without this is only one 20-minute exposure.
Yeah, it's hard to tell.
It's hard to tell. And that's about the best star. This is a wet column, of course. This is better than before. So we are seeing.
Yeah, it definitely looks better than earlier.
Yeah, so I think it was worth doing the Myra, worth spending extra time on this. It's promising that at higher MS with less wind shake, it's going to be better seeing if the conditions persist. No, I mean there's traces in everything.
I think it looks good.
I think it looks reasonable. Yeah. I mean, the feature that's very easy to spot in these red stars is titanium oxide. Not in the raw spectrum, but I mean, once it's reduced, it's got very sharp features like that. You know, I don't have it up on my screen, but you've seen TIO, of course. So. Okay, thanks, Jim. Thanks a ton. Hope you feel better soon.
I think tomorrow I'll be feeling back to normal.
All right. Is home in Waimea for you?
Yep.
All right. Take care.
Have a good night.
Bye.
Thanks, Rena.
Oh. Second 20-minute exposure going, okay. Hey, Kushbu, where are you connecting from? Rob, I'm probably going to stop the recording now. But
Okay.
let me know if you have questions. Oh. Oh, look at this. I've got something cool to show you, Ivana. This is, do you see this dark streak across this? You see another dark streak across this? These are two stars with different velocities. You see another dark streak across this. Whatever these features are, there are different velocities for these two stars.
Which two stars?
Oh, sorry. You see two stars side by side?
I suppose so.
You see this dark streak that runs diagonally?
Yeah.
Because it's at one velocity here in this star and different velocity for this star.
Okay, so that's why.
That's why it's
So
diagonal.
it's serendips, but they're very close.
They're close spatially, but different in velocity. That's a pretty big difference. When you can see that big a difference, that's a big velocity difference.
So do you think that you would be able to separate those
Oh, yeah.
spatially in the reduction?
Should be
Yeah.
able to. Should be able to. Even if it requires a manual extraction, it should be doable.
Yeah.
It's very clear, right? These two patterns are, and this is the calcium triplet. This is calcium. This is the calcium. This is the weaker calcium line. This is the stronger calcium line. I bet we'll see another one up here. Now this is, it would have been in here, but it's hard to see because of this. But with sky subtraction, we should be able to see it. So the way I remember this is this accordion is the center of one of the calcium lines. Okay, so let's zoom out. So this accordion is center of one of the calcium lines. This, I center on this, or if I, let me move up, which was the star that showed the double of this one. Yeah, okay. So 8662 is up here. The second of these pairs, you see these two lines, and then a second pair, this is the calcium, the middle calcium line, and the next pair, right pair of emission lines has the. So when at this velocity, it's quite negative because at when it's at zero velocity, the calcium triplet lands close to this, the lower of these lines. So this is sort of blue shifted by a lot.
Oh, yeah. Overwhelming majority of these targets
should be negative. Yeah,
M32 or
exactly.
M31.
I should have a large negative velocity. Yeah. The disk of M31 is pretty, so, wouldn't be surprised if one of these two is an M32 star, one's a disk star. You can see them separately in velocity.
So are we going to use the pipette to reduce these? Or
We'll do both. We'll do both. Yeah, we'll do both. They're a little bit, yeah, I mean, at least.
I'm interested in learning pipette.
Yeah, so it was very simple to learn. If I could.
Yeah, they have had workshops on it and sent out the materials, so I'm sure I could, if I just made the time, look at those, because I've never learned Spec 2D, and at this point, I probably.
Oh, you shouldn't. You shouldn't. No, even if you. It's a dinosaur. Oh, you shouldn't. Yeah. And it's not supported this way. No, it's not a good thing to learn. But look at the image quality showing us gradual tilt down. You see that? The image quality is definitely going down. I mean, or on average, and that's because the MS is getting smaller and smaller. So I think this is good. And maybe the wind's dying down. That would also help. So after we're done with this, which is in another, I don't know, what is it, 20, not quite 30 minutes, 25 minutes. Let's say we get to 10:15. Yeah, we would then go to, I think we should just keep going down the mass list, even if we don't get to all of them.
That's good. I'm gonna go pace around.
All right.
My legs are feeling weird.
Oh, no worries. Yeah, it's so cool to see the calcium triplet at an angle like that. On the velocity, I'm convinced it's 3 stars, not 2. Yeah, it's a very dense field. Maybe it's not, it's maybe just 2 stars. Yeah, it's 2 stars. Right. But what happens when you have a serendip is it's not necessarily, it's not like the 2 stars are perfectly on the slit. One could be off the slit. So you're sort of getting a fuzzier view of that star because you're seeing its BSF wings. The other thing you see in this region that Kirsten Howley saw in this region is sometimes you see a star and you measure the spectrum and you see 2 sets of calcium lines. Every calcium line is double. So it's got 1 star and another star. Each one is diluting the other's line strengths, of course, but we did that a little bit of deep blending like that. So, Wi-Fi. So this one will end around 10:10. What is that? Oh, that crown. Yeah, Alessandro was wearing that crown. I told him, uneasy lies the head that wears the crown. He was wearing this crown the other day. Rob and Khushbu, do you have any questions for us? We are getting close to the end of our 2-hour session, but if you have any questions for us, please fire away. There's Larissa.
Not really.
Okay, so Larissa's just connecting. I'll ask Larissa to introduce herself. Larissa was just in the room with us, but she's Larissa, please introduce yourself to Khushbu and Rob and tell them about yourself, what brought you to Keck. And
sorry, were you talking to me?
Yes, I was going to say, please introduce yourself.
Oh,
thank you. I know you, but please introduce yourself.
Hey, well, my name is Larissa. I'm a postdoc at the University of São Paulo in Brazil, and I recently received a grant from the Brazilian government to spend 1 year at Keck Observatory, and well, that's what I'm doing right now. I'm working with Jim Like and Randy Campbell with Nove, and trying to learn about all the Keck instrumentation.
Thanks, Larissa. Thank you. Khushbu, did you want to introduce yourself? If you can hear us, or if you wanted to type something in the chat, feel free to. I was curious where you're connecting from and how you found out about shadow. And Rob, what time is it for you?
It is 12:51 here right now.
Oh, wow, late, quite late. 9:51 here. Oh, yeah. You're in California. You said Huntington Beach, if I remember.
No, Los Angeles. We're West Hills.
I see. So we have tonight and then tomorrow night, and then a small break in Shadow the Scientist until we're back on the 30th and 1st, 30th of September, 1st of October. That time we'll be on Lick with the Salvation Project and Monica and a whole bunch of others, Kevin.
That'll be nice to see.
No rest for the weary, but that one is, like this one, this night and tomorrow night I'm heavily involved, but that one is it's no multi-slit mass, it's just single slit, ZTF follow-up, so it's pretty streamlined. We have 11 nights on the telescope across the.
First had to observe in the low. It's just weather was perfect, and I had to basically just like to play. The telescope. Saw that all the images were coming out good.
And it was imaging you did? In the Blanco?
They just gave me a list of some exposures.
I see. Was it the 4 meter, the Blanco telescope? Oh.
They probably take too much.
Initiative, too much liberties. So it's reading out. Hopefully this will be an even better exposure than the last one, but
The RMS is getting better.
MS is getting lower. Image quality should be getting better. So after this one, we'll do one more 20 and then one. So if we finish at 10:15, how much time does that leave us? 10:15? Because remember the end is at 4:35.
DCD
6:20, yeah,
readout
right.
complete.
So at 6:20, can we observe 6 masks is the question. It depends on the scene.
There's also the schedule.
That was deciding the order of the mass, what the angles are, etc. Yeah. The numbers you see after the mass, C1, C2, is the position angle of the mask, and 270 and 90 are the same. And then we wrote down at what times of night those correspond to the parallactic angle. That's what decides on the So even better, the image quality has definitely gotten better. Come take a look. You can see daylight, a little bit of daylight between these two stars that were very close together before. Do you see how you can see just a tiny bit of daylight between them? And they were blended together before. So the image quality is improving, definitely. I mean, hard to quantify by how much, but the images are looking crisper. Each of these is one slit, exactly. The dispersion direction runs vertically. Blue is at the bottom, red is at the top.
That's why we don't.
That's right. That's exactly right. That's right. It's like the definition of a function in mathematics. If you draw a vertical line, you should cut it once. Slit masks are like functions. So Larissa, Rob, and Kushbu, this is how Shadow the Scientist has been running. Larissa, we've been doing this for 2 years. If you have fellow students, could be from any age level, right? You've seen that the Future Hope students are between class 6 and class 11, grade 6 and 11. If there are students you know of in Brazil, Larissa, or any other part of the world, and they're interested in this, in fact, if there are students whose first language is Portuguese and you want to be a translator for them, because you're
in touch with my
yeah, Doug is saying he might involve his high school in this because it might be good for teachers to bring students with them, and we're really trying to contact groups around the world.
Oh, great. I'll definitely send the information for my friends that are teachers and people that work with science outreach in Brazil. I think they will really like the work that you're doing.
Thank you. Thank you. And what I'll do for my part is in the same email in which I sent the Shadow the Scientist link to you, what I will do is I will add link to our program website, the thing that describes Shadow the Scientist. I'll send it to, I won't send it to Jim, and I'll send it to Larissa, I'll send it to you and Doug, okay?
Okay, perfect. Thank you.
So it's a very simple site. It's called Shadow the Scientist. And there's actually videos of past sessions. There's, of course, mention of when the next sessions are coming up. And in fact, I'm going to go one further. Do you use the Keck telescope now? Teresa, you do?
I do, but only with Jim and Randy.
Yeah. So if you know when you're going to use it, if you have an idea in advance, you'll see, if you go to our website that I'm putting in here, you'll see that for each of our upcoming sessions, we create a small Google form. We can help you create that form, in which we put a few sentences that describe what we're going to do on a given night. And then people can register to take part in that night. And they only get the Zoom link after they register.
Oh, okay.
So you can
Oh,
take a
that's
look
nice.
and let me know if you're interested. I mean, Jim and Randy obviously know about this program quite well. Doug is looking for calcium triplet now everywhere. That's calcium triplet right there. Now that you know what to look for, it's so easy to see, right? Yes, calcium triplet. This star has a less negative velocity. So this is so beautiful. Look.
You're using the scope as a reference.
Yeah, exactly. Exactly. See, because this pattern, yeah, I think this is clearly a calcium triplet line right there. Sorry, yeah, but yeah, definitely. You can be a host, in other words, of a Shadow the Scientist. You can connect us to students who you think would benefit from this, but we're looking to do both.
Oh, perfect. I'll keep in touch.
Okay.
To whatever I can find.
All right, of course. Thank you. So what we're going to do, Doug, I'm going to do something fancy here. You ready? Here's what we're going to do. I'm going to zoom in. Oh, see, this has some kind of cosmic ray hit or something on it. There's a faint streak like that, you see.
Yeah.
What I was going to do is take a cut. If I do operation, actually, let me delete all. I've taken a cut, but you can increase the width of the cut. Doesn't seem to be changing, right?
Width type, maybe you need to change that.
Oh yeah. Oh yeah. Can you see the width now?
Yeah.
So what you're seeing,
There's the gap right there when it goes down. Yeah.
this is one of the gaps, but this is probably the other one. This is much fainter. The one on the left is fainter, so you can't see it as clearly. But this is 1 20-minute exposure, so we'll do better. What did you say the gap was? From 10:10 to 4:30 is 6:20. So we should be able to observe 5 masks is what we're looking to observe during that time, not 6. Right, because we finished C1 at 5 masks. I think it's entirely doable. Even if we did 1 hour exposures on each, 5 masks, with overhead.
Is that usually the amount of time you spend for that?
That was nominal. So what we said initially was this thing, we would start, so 20:30 to 4:35. So 4:35 is 28:35, right? And we started at 20:30. Actually started a little sooner than that, but still, let's say we started at that. 8:05. And we said we were going to try and observe 6 master in that time. So we gave us a little over 2 hours of overhead. Now, the first one took us from 2030 to 22:15. So we spent 145 minutes because of the first thing. We spent 3 20-minute exposures before that. We did another. So we did 80 minutes. We actually did 89 minutes of exposure, plus we did a Myra in the middle. So that took up, might do the math right, it took us to 22:15 from 2030. So that's 1 hour and 45 minutes. It's 105 minutes, of which 89 exposure. That's not an atypical overhead, especially because 89, the Myra takes 15 minutes. 89 plus 15 is 104. The remaining 11 minutes is overhead of readout and mask alignment and stuff like that. I think it should be doable. Yeah, if we have to do 1 hour exposures in all of the 5, it may be hard to fit them into 6 hours and 20 minutes. But if some can be cut because the exposure, because the seeing is improving, which it is, it clearly is. I think, in fact, when it reads out the next one, because we're zoomed in, just you see that the things get a little tighter, and especially for those two, you'll see that if it continues to improve, you'll see that. This is my favorite part of the astronomy. Okay, I'm going to hang up my shadow right here. So Mehak, Khushbu, Larissa, and Rob, I'm going to hang up our Zoom call for now. I'm going to hang up. You guys can stay on. If there are any questions, Mehak, Khushbu, Larissa, Rob, let me know.
No, thank you for being there.
Thank you. Thanks, Rob. Thanks for connecting. Bye, everyone. Larissa, see you in remote ops too if you're still here.
Okay.
Take care. Bye.